Good morning, gentle readers. Today is November 16, 2024. From our desk with Ross Finlayson in a study in the research and foundations of logic and mathematics and physics and science is today's Logos 2000. So the previous episode being as from the 10th or so, or last weekend, and as beginning to relay more of an account of the philosophy behind our theory collectively, which is science. As I rose today and shaved, about halfway, and then got to thinking about what kind of topics to consider, then what I thought would be for matters is to get into some of the considerations of the analysis and methods of mathematics. With regards to that, that's kind of the content of some of these other talks here in the philosophical foreground. So in the philosophical foreground, there's some various considerations about metaphysics and physics and the consideration of the questions of metaphysics. And then as with regards to also the combinatorics and the analysis of the finite and the infinite, the infinite. I'll often say finite for the finite and infinite for the infinite. And then as with regards to that is that there's the superclassical notions that have often been the source of both great developments in mathematics, like the calculus and methods of exhaustion and these kinds of things, and that have also been the sometimes anathema to otherwise the disambiguation of things according to the rulio, the regular, which provides matters of the notions of measure and form and proportion, or geometry, the world measure, geo, the world, metry, the measure. So then with regards to geometry and measure, and the world of the logical objects is that usually is considered as of a geometry, and historically that's been the mathematics, and for a long time the second most published work in the world was Euclid's Elements. Then at some point in time, and we kind of point to Descartes and since, but after algebra and the algorithmics, has that the analysis has taken as much of the course of mathematics. And fast forward to since the development of the integral and the differential calculus, and to the time of Hardy's mathematics equating points on a line or a line made of points with those of geometries and those of algebras and those of arithmetics and those of analyses. Then here what is often considered is that mathematics has these different aspects that all are of the same perspectives and projection of the forms that arrive for these various rulialities, the modular, the rulial, the ways that make in these regularities that the asymptotics run out as to provide the perfect analysis. So these are usually considered geometry and number theory, arithmetic and algebra, and function theory and topology, with those last two, function theory and topology, basically having seen the most flexibility in their consideration, and with regards to that which is otherwise is of expansion of comprehension, various subfields of mathematics according to what is a topology, or what is the topology, or with regards to what is a function, what's the definition of function. And so the function theory and topology then make for the operator calculus and analysis. They usually analysis is central as for setting up all these things, and then it's relayed in terms of algebra as almost ubiquitously for all matters of formula, vis-a-vis number theory as for quantities and geometry as for forms, that number theory and geometry and algebra and arithmetic and function theory and topology then make for analysis in the operations or the operator calculus, that's mathematics pretty much what there is of it. And that also each one of these aspects model each other. Our proof theory is a model theory. So in the analysis, what ends up being the case is that there are any number of ways to look at the standard and the non-standard as if from the law of small numbers, and then what's not true about small numbers to carry out, and then the law of large numbers that they behave as essentially unboundedly many small numbers to then some unboundedly many larger numbers, then for these laws of large numbers, the infinite numbers, as with regards to these things. If there's one example that can be made to show that the inductive analysis does not always arrive at the conclusion that is so guaranteed, it's this. And this is that the ratio of a circle's diameter to perimeter is pi. And so if you consider the diameter of a circle and bisect it, dividing it into two equal pieces as of radii that reflect each other, and draw circles in those, then those half lengths also have to keep the same linear relation of pi. And so the circles with their diameters, those radii, their diameters, make the circles with the same perimeter, their sum. And so dividing that again and again and again, it maintains that same perimeter sum to the same diameter sum. Now, as that's repeated ad infinitum, what results is that the circles get smaller and smaller and smaller until in the limit, all that results being left is the straight line. And then no longer is the perimeter equal to the diameter, because the perimeter and diameter are related by pi. So as you can see, a course of induction would arrive at is the same, but a course of induction as where it goes, as where it's already given, that the result of those vanishing, those differences from the line is not the same. So this can just serve as a particularly tractable and graphical example that there are counterexamples to otherwise the inductive inference in these means of exhaustion. And then it also gets into a great many of the things with regards to the continuum analysis and the doubling and halving spaces, this pi rationing space. So that helps a lot to at least open the door to what would otherwise be a walled garden of sorts, a paradise, if you will, of the plainly unconcerned with these otherwise guarantees, their constancy. That in this manner, by drawing the yin-yang symbol and carrying that on out and down to where it's via means of exhaustion, that it's shown to go to the line from these semicircles, has that then in the limit, it is not the same as the inductive course, while at the same time, in the limit, it is as of this way. So that's ultimately true in this manner. So I hope that would serve as a particularly accessible example of what otherwise does not have so many examples, because otherwise that's apeiron, or it's just not considered in the ad absurdum to arrive at something that's perfectly related, while at the same time it's not the ad infinitum, which is that it is when it is. Usually, as with regards to the geometric series in the half and half and half again, does sum to equal no different than 1. So looking about a bit, let's see here. Well, I thought I might adjust Lincoln back here a bit. He's been sitting kind of in the back. I think I ought to move him up front a little bit. Just so, it doesn't seem that he's of a particular distance from what's regarded as part of not so much the technical, but the social. And if there's one thing it said for Lincoln, is often he's everybody's, in an American sense of egalitarian and individual liberties with regards to Montesquieu and Locke and these philosophers that kind of arrive at some of these reasons why it is so that in the progression of history vis-a-vis the cycles of history, that it's considered the best and the fairest and the most appropriate for a civil meritocracy of like-minded individuals, each distinct and each unique. That said, then there's also a certain particular affinity here for him because of some distant relation, as if within the past couple hundred years, great grandpa was his cousin in the same county or what, so it's considered Uncle Abe, and he's held up in very high regards. And then behind him there, for no other reason except in line, is that's Georg Cantor. And I don't have any particular affinity or relation for Georg Cantor, except with regards to his great emplacement in the mathematics as for the Maugin, the set theory, with the transfinite cardinals and the Aleph numbers, which are, as with regards to the modern mathematics of the day, having established a particular linear course that after Russell's retrothesis and a particular restriction of comprehension, which is not a truth, has arrived at a sort of the halfway account, according to this inductive argument, which is we've just observed. There are counterexamples of infinity in the numbers today. And then furthermore, these days we have the larger numbers and laws of large numbers, as with regards to Kant's sublime and which is greater than itself, with regards to things, the ding on sich, which is in itself, as with regards to Kant's establishment of analysis as on its own grounds, as after Descartes and Leibniz and Spinoza, that analysis was at least as of an inkling of a thing, then for that analysis that the logical analysis is a very full and wide dialectic here, and that it so intends to convey that it's available to each by the reasoning apparatus. And then for Kant's noumenon and phenomenon, that the noumenon includes an object sense, a word sense, a number sense, a time sense, and a sense of the continuum for any matters of reasoning and analysis, that it maintains a connectability to a brief metaphysics that, according to Kant and Hegel, are, of course, still kept enshrined within the theory, and that as well, according to reason, may be kept to exist, even about the tumult of all the various philosophers that do or don't have it as very accessible to reason, either themselves or more generally, that it is considered accessible for itself. So the metaphysics in this manner are so related, and as part of a theory with a teleology and an ontology, and all quite strongly logical positivists, and not weakly, and all quite strongly mathematically Platonist, and not to be like fide Platonist, vis-a-vis deism and fideism, and the notions of the super scientific, the super sensuous, the super scientific, that our noumenon can still reach these as with regards to matters of contemplation and deliberation on the origins of reasoning and this and that. One of the greatest examples of that is kind of with regards to the geometry in space, of points, spaces, geometries, and then the space of words and the discrete, so that the geometry is fundamentally continuous and words are fundamentally discrete. And so, like other matters of works that would intend to convey at least some aspects of the technical philosophy, the Old and New Testament, then we have in that the most published book in the world, that it begins with this account of how space arrives, and then it has in the middle an account of how a word and language and communication exists, that these are given as, if not axiomatic, plainly just evident. So these are then also accounts as of the axiomless natural deduction. It's not dissimilar. Some of the Vedas, the story of the Atman and Brahman of the Vedic and the Indic traditions, that these are thought experiments of matters of perspective and projection, even technically. And so it's usually considered more as with regards to enlightening thought experiments of the mind, and that these are traditional and as part of the oldest traditions still extant available, that it as well is technical. And so matters of projective geometry exist according to these. So what I thought today to do is to look back a little bit at some of the analysis where we left off with the study of the Fourier-style analysis. So the Fourier-style analysis has some interesting aspects to it with regards to it's after the invention of the integral calculus and the differential calculus. And so what that means is that after the geometric series and methods of exhaustion since antiquity, then there arrived that there was the calculus. And so we were able to then use, basically for power law, and then for various forms of integrals and differentials that in the functional framework make for the integrals and derivatives or functions. And as for functions, and it's analytic in this setting, then there's a lot to be then figured out what goes on into the Fourier analysis, because it makes for all these different ways to have the reductio and the reductio again, because the analysis is as if taken apart and put back together as of vanishing sums of vanishing sums. So if our analysis today is after Weierstrass, then for Cauchy and for delta epsilonics, and then for Riemann sums and for Riemann and Lebesgue measure, then it's as well that in the Fourier analysis there's a double reductio then of this again to arrive. And then we have the Fejer and the Dirichlet kernels in the usual formalism, and that these have to result in making for these what's non-standard by the time it's put back together, the Fourier-style analysis. And then there's various notions that go into whether the uniqueness of the trigonometric series in these things is a thing, and how that's arrived at, and that's as was considered here. And we're going to take a look at Gonzalez Velasco's book on this with regards to the standard way that Fourier analysis arrives. That then after that much like the Eulerian, Gaussian, de Moivre complex analysis just being everywhere and people having forgotten to ever look that division could be defined two ways, and this is that the Fourier analysis and its derivations have for Dirichlet that then Poincare was quite all about in this space, in the analysis, keeping for sure that then it doesn't make for so that some particular results which are decided to rule or decide within the Fourier-style analysis carry out through all the wider analysis and the analysis that would otherwise make mathematics hobble itself. So taking a look here, it's Fourier analysis and boundary value problems. See what we've dog-eared up to this point. This includes the maximum principle for the heat equation. And so we've been talking about the domain and continuous functions. We've got past the Gibbs phenomenon and how it's explored that there's a particular dimensionless ratio that arrives from after that. And so with some of the things that we have going on besides the sinusoidal, the hyperbolic sinusoidal, and then also with regards to the sigmoidal, there's been some more considerations since the extant deliberations in the descriptive differential dynamics of the theories of the heat equation or a heat equation that gets into some of these other ideas that we're going to try to pick up from where was left off here. So we have Weierstrass and then convergence criteria. And so the convergence criteria make for another example of why the yin-yang example ad infinitum is counterintuitive. And a counterexample to inductive apparatus is that in the establishment of convergence criteria for series, in the infinite series, and whether they are convergent and have a limit, and thus attain to and reach this limit, in the infinite or in the asymptotic, has that it's known these days that some of the simpler and naive criteria for convergence fail, and thus it's guaranteed that in the description that they can be accorded to being distinctness results when they do succeed, vis-a-vis uniqueness results that they never fail. And so that's a thing that is part of the wider analysis of the mathematics. And absent it is still possible to employ many possible means to gain value and to obtain from the mathematics, yet it is not complete. And furthermore, it can arrive at the inconsistent. So in the wider complete, we have multiple laws of large numbers. This is after multiple domains of the continuous domains, a continuous topology for each. And that then as well with regards to the Cantor space of all the zeros and ones, there are at least 3 of them. With regards to this potential, effective, practical, and actual infinity, which is a thing. Let's see what we have here. So we have where we left off reading here, and it was back to the example of a plane ansatz, the heated bar. And there was some talk about Weierstrass. Oh, and Heine. Heine discovered this, and then with Kant, or as with regards to who this discovered this, and then that with regards to its uniqueness or distinctness, that here for the Poincare rough plane is established this kind of thing about the yin-yang ad infinitum, that it's kind of like, well, is the diameter smooth, or do all the inflection points on it add up to that it's the same length as the perimeter? It does not. And so that besides that making a great counterexample, an accessible counterexample graphically as well, then there's also that the Poincare's rough plane is a lesser explored altogether idea with regards to the grain and the graininess of the smooth and the continuous. So then that's here is with regards to the doubling and halving spaces, and then it's with regard to this pi ratio space. Mixed endpoint conditions, initial and boundary value problems with regards to the differential analysis and the superposition of solutions which are established after usually excluding the trivial or zero solution. And then it's so much made up of the exponential solutions, which then out of their differential course arrive at just linear components, that this then makes usually eigensystems. And then out of those, then the Sturm-Liouville conditions quite usually make for the uniqueness results of solutions. And then as after superposition, they can be summed by any number of means to arrive at any possible solution. Then that plugging back in the initial and boundary value conditions make for solving for examples of those which suffice as solutions. Then have it so that the there's checks that have to follow that. So that's just part of the usual grab bag toolkit of the differential analysis that's been relayed in these talks, and it's the practice, because what arrives at that is that these uniqueness and existence results must so be to carry out in this way. It doesn't exclude that there are others. It just says that in this way there are these ones. And then furthermore, after it's solving for reasonable or real value or real analytic, usually the checks of the solutions, that it helps to establish that there are cases where otherwise they fall out what would be nonsensical, or as relating a wider singularity that what would otherwise be the solutions. So, time-independent problems. In the preceding sections, we have presented just a few boundary value problems for the heat equation. A variety of other problems can be obtained by choosing either a more general equation of heat propagation or more general endpoint conditions. For instance, if the cross-section A of the bar remains constant, but the specific heat capacity C, the density ρ, and the thermal conductivity K of the material are functions of X, rather than constants, if there's internal heat generated at a rate Q that is also a function of X, if we write C instead of C rho for simplicity, then the equation of the heat propagation is C mu1 or mu t equals k u x x quantity x plus q. In D equals this xt in r squared, 0 less than x less than a, t greater than 0. We assume that c, k, and q are non-negative continuous functions on 0, a, and c and k are positive, and that k is a continuous derivative. So this is a great thing because it helps introduce the implicits to the algebraic. Because much like otherwise the derivative is considered the slope and the integral is considered the area, that they're kept as functions because there's always implicit in them. What are these implicits for the algebraic quantities to be so derived and derivable that it is so that they are as well conditions that reflect that if they are so reflective and symmetric, these implicits which make for the derivation of the quantities, that otherwise abandoning that difference at each step in the algebraic manipulation or the formula as it's written in each formula or theorem as it's usually in place, as in a case of the algebraic development, that it is definitely to be retained these ideas that the implicits are actual and the implicits contain the nonlinear effects, so the non-standard contributions, those things that do make it so then that these other examples that belie finite inputs in their infinite course are yet mathematical. It's ad infinitum, that it is so that after these convergence criteria, then we can figure out the emergence criteria of these things. So it's warmly appreciated that Velasco's book here gets into detailing this so briefly, yet conveying in it then is like, it will always be part of the context after this, that these implicits are part of the context throughout. As for the first hypothesis, we shall work under the following hypotheses. Our coefficients are non-negative constants. We'll arbitrarily say that they're ordered to maintain their order throughout, and that gets into when there's symmetrical relations or things that oscillate and thus attenuate or oscillate or then are constitutive. This is the adiabatic case. It's not diabatic, adiabatic. Vis-a-vis the non-adiabatic cases that would arrive when it's relevant whether these two terms that are otherwise just arbitrarily left to say that it will always be so that A less than B, A vis-a-vis B. So, unfortunately, the first hypothesis will also rule out some well-posed problems. As, for example, when A1 equals 0, B1 less than 0, and C1 greater than 0, for this choice simply means that the heat leaves the bar at x equals 0 at a constant rate. This is permissible, but such types of problems should be posed with extreme caution. For instance, and this is the envelope. This is the edge of these things. For instance, if in addition A2 equals C2 equals 0, the bar is insulated at x equal A, and it can lose heat at a constant rate at the other end only if heat is generated internally at a sufficiently high rate. So he's indicating that there's a criterion for the implicit to be fulfilled that would otherwise just be a drop-off or a cutoff is instead a floor. Even this may not be enough if the amount of heat initially stored in the bar is insufficient. And so he's relating in terms of these physical quantities what's going on into the mental modeling of this dynamical system. Therefore, we reaffirm our decision to work under the first hypothesis, but in some of the exercises in this section, in the case in which B less than 0 or B2 less than 0 will be explored further. The second hypothesis is included, and this is that the A1 plus B1 greater than 0 and A2 plus B2 greater than 0, to make sure that none of the endpoint conditions is missing, since we cannot expect the problem to be well posed without one of these. For example, if A1 greater than equals 0 and B1 greater than equals 0, the inequality A1 plus B1 greater than 0 guarantees that these constants are not both 0, as this would imply that C1 equals 0, and then there would be no endpoint condition x equals 0. Or when saying that there's no endpoint condition, that it would be, at best, an indeterminate quantity and something else would have to be in place to make it so that it can be said to share the same derivation. The case in which A1 equals A2 equals 0 is very delicate. When C1 equals C2 equals 0, the bar is insulated at both endpoints, and the temperature is expected to rise without bound unless Q is approximately on the order of 0, the triple equals bar. This is also true even if Q equals 0, if either C1 greater than 0 or C2 greater than 0, because now, according to the second hypothesis, we have B1 greater than 0 and B2 greater than 0. And then heat is entering the bar at a constant rate at one or both endpoints. To verify our physical intuition, we shall investigate how the total amount of heat in the bar varies with time. We have the integral from 0 to A of C big AU ST ds, that d dt. So the integral in ds over the bar, or from 0 to A, the constants times u, the function in time. Differentiated according to time equals big A, taking the constant out in front, u to A, CUT, ST ds equals the integral of A quantity or A times the integral from 0 to A of this quantity KU sub x, so then the formula in x, because this has been separated in terms of the time parameter and the second order space or distance parameter, the Fourier's heat equation, ST plus QS, that quantity times ds. And so it's shown that he's put in place like the additive term, and what was otherwise as a constant that would have to be kept into it, and then it's integrated all across that. He says that it equals A times this quantity KUX AT minus KUX 0t plus the integral from 0 to A of Q, which should be a constant itself, or is that it's a function, and it equals A times this quantity KA C2 over B2 plus K0 C1 over B1 plus integral from 0 to A of Q. And so those can't be indeterminate forms, and whether they are or not, or whether they exchange places, or whether there's sometimes a demon is said to exist, and what does it do? It's like it does anything arbitrary that otherwise you don't have a physical explanation for. Maxwell's usually, or Carnot's or Planck's, these ones. That here it's that this organization makes for then these implicits, and why it's usually simplest to then make it so that it's not well posed and it's not well formed, these problems, when otherwise these implicits are at all non-negligible, and that they are formally non-negligible. Hence the heat will increase without bound unless this derivative is 0. Since A, K, B1, B2 are positive, this is possible only when C1 equals C2 equals 0 and Q equals 0. This justifies the third hypothesis if a bounded solution is desired, because otherwise it would be just another function, and then it would have to be in terms of a reification of the initial or boundary value problem analysis. Note next that this general boundary value problem contains all the previous ones. When C and K are constant, Q equals 0, and B1 equals B2 equals 0, we have the problem of section 3.1 or section 3.3. If instead A1 equals A2 equals C1 equals C2, then the bar is insulated at the endpoints. Finally, with the choice of signs in 15 and 16, so that's the choice of signs is the relevance of saying that we'll turn our diagram either way according, so it just lines up that way. The choice of signs in 15 or 16, we have convection at x equals 0 when A1 greater than 0 and B1 greater than 0, or convection at x equals A when A2 greater than 0 and B2 greater than 0. What we have learned in these particular cases allows us to outline the following general procedure to solve the boundary value problem and to verify that it's well posed in the sense of Hadamard. Then he gives some exercises. Find the steady state solution, find the transient solution, find the complete solution, verify the uniqueness and stability of the solution. These 4 aspects of the problem will be studied in the next 3 sections. So just establishing that this setup gets into all these different cases, and because each one of these has these flexibilities in the parameters, then just goes to show that the configuration of the experiment and then the energy of the experiment lead to many, many different kinds of ways to interpret mathematical models and mechanical models and physical models in the setups. So what this reminds me of a lot is the nonlinear electromechanical effects and applications. So the nonlinear electromechanical effects and applications is a book by G.A. Maugin, Gerald or G.A. Maugin. And in it, he puts together each of these things that go into the electromechanical, and as with regards to non-negligeable terms, and he introduces into the formulas and what would otherwise be the algebraic derivations to get past what are called these anomalies, something that's against its own name. It's anomalous. It's like, well, it's supposed to be linear. It's not. It's supposed to be constant. It's not. It's supposed to add up to be like so. It doesn't. So this is called the anomalies. And then in the course of that, what he arrives at various ways to parameterize the forms, to make for the implicits, to provide explicits, to reformulate the formulas in terms of these other functions. That is part of the course of Maugin's development. And what he shows is after this tensor analysis, and with the Piola-Kirchhoff tensor, which is a way to maintain the conformal and the affine as of otherwise after vector addition, which would be the tensorial products, that this way, and then in a brief attachment to a convolutional setting, or otherwise setting up for the non-adiabatic, the diabatic, vis-a-vis what's otherwise like in this heat equation, the adiabatic, that these kinds of things really get into a lot. Why it's a part of higher mathematics in the analysis to make it so, to get what otherwise are all these kinds of indeterminate forms and the way these things could or could not be, that the guarantees exist, and that there are ways to do this, as after Gonzalez Velasco put it, a delicate situation, fragile, tenuous situation, that thusly it as well, it becomes this ironclad guarantee of mathematical truth and a mathematical fact. So that's some of the analysis I wanted to get into today, as with regards to these things. So here's Einstein and Infeld, and this after talking about Maugin and the nonlinear electromechanical effects and applications, and how that today is used to implement things like these simulated quantum computing, which are superpositions of states that all add up in like a giant flow machine. It's like taking a field programmable gate array that's wide and parallel wide and running it across and having it run out and compute in parallel wide all these solutions at once. Like the D wave is implemented by this surface acoustic wave transducer that Maugin and crew developed mathematically 30 or 40 years ago. It is simple. This novel silicon design of such matters of the simulated quantum computing, which so many people hear about as quantum computing, which is not. That these are the kinds of things that get into the fields in the electromagnetism. So this book by Einstein about the electromagnetic it says it's the ideas from early concepts of the relativity and quanta, but it has a lot going on with the fields with regards to the Maxwell's fields and the Lorentz invariants, and then that here is usually framed in terms of Faraday, Heaviside, Larmor, and Fitzgerald, and then Maxwell. So all the stuff from the potential fields and the 19th century, the 1800s electromagnetic theory that then was bolted down to E cross B or D cross B variously, whom you ask, the classical magnetic fields that arrive at electromotive force, particularly, that then potential and Ohm's law and Kirchhoff's law are so simple as vis-a-vis how then it's in a sort of reverse engineering added back up from linear to Weichardt potentials of test particles of electron holes according to current given coulombs, amperes, that this book then might have something about it, the electrical fields, because then otherwise relativity theory of relativity of motion is rigid bodies, and then also as with regards to the wave fronts. The electrical field is a standing field everywhere. It's like a vector field with 1.0 everywhere instead of a space according to gravity's placement of objects with 0 everywhere, and temperature with 0 everywhere, and this kind of thing. That it helps to reflect that the electrical field is just that much different than the field of gravity. And he's talking about waves, the decline of the mechanical view. Let us consider a portion of such a sphere at a great distance. So that would be kind of like at a great distance, or a large sphere. Its outside its curvature is 0. It's flat. It's a wall. It's like a cube wall. But yet from inside, as a circle goes small, then it becomes the circle's radius makes this curvature is entirely curved. Until at the end, as we just talked about, this yin-yang ad infinitum becomes flat again. So this cube wall is the idea to help reflect for the Schwarzschild metric and the event horizon, and Chandrasekhar and the classical formula built off the classical formula of gravity for the gravitational singularities. That it is part of the tensorial product that is in this way geometrical. And then that gets into the fundamental units of mass and length and time with regards to density, and the very small is part of continuum mechanics again, and this quantum mechanics, the particle theory, the points, the point, the local of the global and the total. The wave theory of light. Now, a comment here with regards to, yes, I say that optical and light is not electromagnetic, and that electrical and the magnetic is electromagnetic, and that both happen to have wave properties defined about by the frequency and wavelength. Then also as with regards to the intensity and the energy of those, then intensity is always left out. And then why it's frequency and wavelength for both photons and electrons, which are not the same. An electron has charge and a little bit of mass, and a photon's got 0. And the poor photon has been diluted and overloaded with umpteen definitions for every single aspect of quantum electrodynamics. So when I say that, it's on purpose, and it's to be reflected that anywhere else in the theory where it's said to be otherwise is part of the theory itself. That's a kind of a thing. So the wave theory of light. The wave theory of light is usually we point to Fresnel as I point to Fresnel as one of the greatest theorists ever with regards to that. And then there's Huygens about waves, and those together made it so that it was not just rays and not just particles, and that it was waves. And then for the optoelectronic effect, that's what Einstein kind of gained his great fame, was for the photons and electrons in the optoelectronic effect, which is always at a junction. It's always that they're equivalent in energy before and after the junction, not as of otherwise that absent the junction that magically appears this way. There's no such thing as that. As far as the combined theories go together, and there's the notion of the Dirac positronic sea, kind of this rough plane of these things, that where it's not entirely unsensible with regards to the Zollfrei or the white hole sea or the positronic sea of Dirac and Einstein. That the wave theory of the propagational light, it also adds up for all these things about de Broglie. and whether electrons also show the same diffractive behavior is with regards to them standing in the electrical field. They're also as well waves, and so they both have wave models. They don't necessarily live in the same wave model, and so it's only kind of contrived when either light interacts with light or the electrons always interact with electrons, and then whether light and electrons interact is per the medium of these things. It was Huygens, a contemporary of Newton, who put forward a quite new theory. In his treatise on light, he wrote, "If, in addition, light takes time for its passage, which we are now going to examine, it will follow that this movement impressed on the intervening matter is successive, and consequently it spreads, as sound does, by spherical surfaces and waves, for I call them waves, from their resemblance to those which are seen to be formed in water when a stone is thrown into it, which present is successive spreading of circles, though these arise from another cause and are only in a flat surface." So waves here are just a general medium of a milieu of the modeling of the exchange of the radiant in open systems, or modeling of change in open systems. That it's waves is particularly accessible because everyone has explored making waves. And so if there's one thing I'd like to mention, that is that an important learning setting is the opportunity to find a rocky beach and upon it to find such stones as are flat and thus can be made to skip the rock. What this is about is that given a smooth surface of a lake and a stone, then one can throw kind of sidearm and impart to it a spin, so that it says of a spinning disc, that the stone will strike the water and skip again, and skip as any number of times which can be possible, which is the goal, to give it the maximum number of skips, skipping a stone across a body of water. And this takes a very particular configuration energy of an experiment. You got to find a configuration of the stones that are the right shape and the right size to be so thrown, and a particular energy and configuration of the body of water that is smooth and offers a surface that can provide so that stones can skip. And it helps to have some examples of people to emulate who are able to make a good number of skips. That is generally guarded that anything beyond 7 good skips is a very, very great stone skipping throw. And while that's possible, it's possible sometimes to see them arrive at the end of very many small skips, not necessarily quite skips. I've counted up to 28 small skips in a stone's throw. But reaching 7 takes a particular amount of practice. And otherwise, it's just kind of a plonk, or as with regards to that being an experimental setting that all of the people who ever read this book in this time and place would have known about and practiced. According to Huygens, light is a wave, a transfer of energy and not of substance. We have seen that the corpuscular theory explains many of the observed facts. So the wave that's the image so formed by light is a matter of information. And with regards to the discussion of the free, if metered, transmission of the signal, of the image, the optical image of light, it's not merely energy as by intensity, it's also organization, and is with regards to the infinite frequency of coherent and non-coherent light, and that otherwise these considerations of the wave-like, the particle-like, the photonic, the radiant, and the beams and the rays of the geometrical and of the optical all are part of this great milieu of why optical light is special, visible light is special. And that the electricity is otherwise considered that the only image it conveys via signal is the highly contrived and the very organized and is entirely precise, where light will go through anything, pretty much. According to Huygens, light is a wave. We must again ask the questions which have already been answered by the corpuscular theory to see whether the wave theory can do the answering just as well. We shall do this here in the form of a dialogue between N and H, where N is a believer in Newton's corpuscular theory and H in Huygens' theory. Neither is allowed to use arguments developed after the work of the two great masters was finished. In the corpuscular theory of the velocity of light, it's the wave front. And then there's much made of this model of sound waves, because sound waves, first they show Doppler, and they show that for a finite, they have a finite and various media fixed transmission speeds, which according to the technologies and the precision available at the time could be established reasonably. So the acoustic model is for the transmission of light and its flux, much like the electrical model of flow and the fluid model of flow. While that is so, there are sides of it that are entirely opposite. The skin effect of the electrical current is entirely opposite the core effect of fluids and liquids. The various acoustic and the optical as acoustic, and the acoustic as the optical with regards to reflections and these kinds of things, and with regards to diffraction and refraction, has that light as diffractive. And as with regards to sound waves, that is its own sort of consideration, in a sense. That being largely kinetic and kinematic, the transmission of sound waves, as with regards to otherwise optical and visible light, is fleeting and flux. And that it does represent a milieu of the maximum propagation. And as with regards to information and signal, yet they represent successive milieus, and that on the outsides they're completely different, vis-a-vis having some shared intertendency or modeling each other, and when they don't. So that's something to figure out. In the first place, it introduces a new hypothetical substance. We already have too many substances in physics. There is also another reason against it. You no doubt believe that we must explain everything in terms of mechanics. But what about the ether? Are you able to answer that simple question as to how the ether is constructed from its elementary particles and how it reveals itself in other phenomena? And the Huygensian says, your first objection is certainly justified, but by introducing the somewhat artificial weightless ether, we at once get rid of the much more artificial light corpuscles. We have only one mysterious substance set of an infinite number of them corresponding to the great number of colors in the spectrum. Well, you see, it's a restriction of comprehension. And so it's not a truth, it's just a course. And then it has its own truth within it, but there's a greater truth without it. So that's disusual forever. Do you not think that this is real progress? Well, here this is in the past. So there's something to be said for the ether hypothesis, which is that space exists. That besides the usual notion after Einstein's theory of relativity that there's curved space-time, and so that there's no real just like space by itself, and particularly that the electrical field doesn't live in space by itself, that the electrical field must be somehow kind of its own thing, has that the ether hypothesis is kind of this space where it's, according to here, it's general relativity and real space contraction, Fitzgerald and Lorentz and the Galilean. That this one then of the usual simpler general relativity does not have this thing at all. So for many years, because the ether hypothesis was how all this 19th century electromagnetism theory was built. And then a lot of people, after the modern account of the Maxwellian and Lorentzian, were told it's like the ether theory is not just that the ether theory is no longer a working milieu, but that it doesn't exist. So this is bad because it's as of taking a theory and making it privileged. And we know from general relativity and special relativity that there is no privileged frame. So when there's a manner of speaking where in one theory and the other theory that they both have and model the same things themselves, and it's said that one, the other doesn't exist, that doesn't exist. It is simply simply a kind of a reflexive rebuttal, a refutation of that sort of approach, because you can close your eyes, you might even be able to close your ears, but you cannot close somebody else's mind. And so, with that said, the point I wanted to make at this is that the ether hypothesis, that there exists an ether, is not necessarily compatible with other mathematical models of relativity with regards to electromagnetism. And that's fine. That's the way it is with regards to our classical Maxwellian Lorentzian, I said classical, but our Maxwellian Lorentzian electromagnetism. Yet there are theories like the Larmor and the Heaviside and Fitzgeraldian and the Faraday. There is an ether theory, and particularly in Einstein's Sidelights on Relativity, which he wrote about 1920, which you can find online, for example, in the Gutenberg Project, as it's out of print and accessible to everybody. In Sidelights of Relativity, Einstein has a brief article on the ether and puts forward both that it may exist and that it does. So Einstein, for whom people say that, well, because of Einstein's theory, there's no ether theory, has it that Einstein says there is. So Einstein's wider milieu and his later maturing, more inclusive theory is better with regards to these kinds of things. So then this just gets into a usual set of interlocutors discussing these things, talking about parallel displacement, a plane wave, diffraction, modeling diffraction in the finite element analysis. So with regards to spots, and then we talk about the ergo spot, which is like, it's like a condenser. When you shine a tube and you expect that all the light would fall on the outside, there's a spot in the middle, the ergo spot, ARAGO. The ergo spot is a readily demonstrable experiment to show the superclassical behavior of visible light. We shall use the dynamic and not the static language in the following pages, bearing in mind its limitations. And that is to say, static and dynamic are different perspectives for projection upon each other and about each other. There are both sides. And in this section in the chapter field, relativity is general relativity. There still remains one point to be cleared up. One of the most fundamental questions has not been settled as yet. Does an inertial system exist? We have learned something about the laws of nature, their invariance with respect to the Lorentz transformation, their validity for all inertial systems moving uniformly relative to each other. We have the laws, but do not know the frame to which to refer them. Well, yeah, Einstein's later theory of relativity at least says it is an inertial system. And so that's what he arrived at sometime after this. So this was written a bit before, out of my later years, say. And he talks about an inertial system in which the laws of mechanics are valid. Then with regards to frames, the terrestrial frame and our solar frame, and that being in a neighborhood, a region of the galaxy, and that being larger, it reminds me of this quote of Aristotle. And he says, circular movement is eternal. And it reminds me of this other quote of Aristotle. There is no unmoved mover. So how can these agree? Then what that gets into is when we get into the wider, the total field theory, it's called Mach-ian again. So for Mach is associate all this stuff to do with the acoustic. And then Einstein is like, I gotta be Mach-ian again in the total. Because Mach was like, well, I'm thinking outside acoustics. And so Einstein later develops this fuller and wider milieu. So that yes, there is an ether hypothesis to go along with the clock hypothesis, and then that the usual mathematics of relativity given as Minkowskian space-time and the Lorentzian is a particular representation of some conservation and continuity laws, and a mathematical model with some free space about the variables, so that bookkeeping can be kind of set up for matters of perspective and projection when they let in or let out. And then also it just makes for some simple rules and inequalities, kind of as we were discussing in the well-formedness and well-posedness of problems, to keep some things computable and sensible, fungible, and tractable. Well, that's about today's course of this Logos 2000 21st Century Foundations, including all the previous centuries' foundations, that comes up with some more examples of why there's a plentiful course of these historical treatments that arrive again. And then it takes a deconstructive account, because otherwise they get stacked up above what's otherwise the foundational elements of the platform. It just becomes wider and more disparate and longer and narrower planks of the theory that do not work out at the end and become very, very too much fragile, tenuous, and unguaranteed, which is why this deconstructive holistic account for complementary duals in the monism of the holism quite altogether is sort of required then to arrive at this greater milieu, or 21st century foundations. Well, gentle readers, fellow earthlings, I shall so hope that this is useful for you, and that it will give some examples of some ways that you can find yourself as of knowing more about theory and how it can arrive via reason, all these things. It's all one theory.